everyone. Can everyone on Zoom hear us? If you can't, please write in the chat. Okay, I got a thumbs up. Great.
Got it.
Thank you. All right. Thank you for joining the Athena seminar series. Today we will hear from Jiwen.
Yeah, Jiwen or Aaron.
Jiwen,
Yeah.
Aaron Fan.
Fan.
He is a PhD candidate at UT Austin.
Yes.
Advised by Professor Atlas Wang.
Yes.
From Athena. He was funded by the Qualcomm Innovation Fellowship in 2022 and is currently a research intern at MetaCore AI, developing 3D foundation modeling tools. Jiwen has also interned at NVIDIA and Google and previously worked as a senior research engineer at Alibaba Group.
Yes.
Thank you. Welcome.
Thank you. Thank you. Good afternoon, everyone. Really thanks to Professor Chen, although he's not here, but thanks for the invitation to this fantastic place. So today I will talk about scalable 3D and 4D asset creation using generative AI techniques. So we will cover the topics from using generative techniques for computer vision and especially for 3D or 4D. And we will also talk about how can we build a lightning fast pipeline for the 3D asset creation. Yeah. So the rise of 3D asset creation enabled by artificial intelligence allow us to generate high quality 3D models from very simple inputs like the images, like the text descriptions, or from the panorama image. So they are driving the industry from the extended reality to robotics, to gaming, and to the urban planning. So now the market is quite booming and expected to reach $33 billion by the year of 2025. The technological innovations in 3D representation, including the neural reading field and the 3D color splitting, are driving the change. So let's take the 3D color splitting as an example, which is a state-of-the-art techniques. So they are a kind of explicit 3D representation, and they model the 3D space by each primitive. And it enables the creation of the photorealistic 3D environment and enjoy the real-time rendering speed, which is a significant leap than previous methods. So let's take a look at a specific example of how this generative AI can be used for the real case. So start from a physical world, and such as this beautiful historical building, and we begin by capturing multiple images. So that these images is they are amposed and they are uncalibrated, and we don't know where we got this capture, right? So listen to the reconstruction pipeline. We denote it as F. And these images are stitched into together, allow us to recreate the 3D space. And to the user end, what we can see is a navigable 3D representation, and we can interact with and we can play with for many downstream applications. So that's a basic streamline outline of the 3D reconstruction pipeline. Yeah. So however, even the cutting-edge neural 3D reconstruction techniques still demand many images for the reconstruction. Let's say we have to capture hundreds of images to build a photorealistic 3D environment. So that's a major problem of the current 3D learning techniques. So we may ask, why are so many images required to build the 3D environment? The basic or the nature of the answer lies in the complexity when we're trying to recover the 3D structure and appearance from image observations. So first, it requires a multiple step processing when we're trying to recover the 3D information from images. The first step called sparse reconstruction. Given these images, we use them to analyze and estimate the camera pose. And we got the camera pose, and we also get a sparse structure of the entire thing. They provide us a preliminary results, preliminary structure of the 3D environment, but they are not dense enough, so they cannot physically or plausibly represent the 3D environment. So that's why we have to use the second step called dense 3D reconstruction. So the dense 3D reconstruction trying to complement the 3D environment with more and more 3D primitives, stuff like that. So this process is called densification. We densify from sparse point cloud to density one, and then we will have a photorealistic 3D environment. Yeah. So therefore, to answer this question, so more images means more data, and having more data, we can have better camera pose estimation, and then we can better complement the 3D environment using image information. Yeah. So this is a very intuitive example. So start with multiple images. The first step give us a set of initial point cloud, and we also were aware where we got these captures. And the second step, we're trying to densify this sparse point cloud. And finally, we got this dense representation. We can run the non-view sensors, but of course, we are still 3D. We are recreating the 3D space. So that's indeed how we represent the environment. Yeah. So if we going to understand more details about the 3D representation, let's take one example about here. We can see one 3D primitive. So for each primitive here, it is represented by its position, its scale, and color rotation and opacity. So having this mounted on each 3D primitive, you can think we are trying to use a 3D Gaussian, and this 3D Gaussian is placed in the surface of the 3D environment. And we have many of these 3D primitives. Finally, we can represent the photorealistic world just by optimization way. So however, if we transition from dense data or dense images to sparse data, so we can see if it's dense data, we have so many point cloud as initialization. But if we use only sparse data, we have way less initialization, and the camera pose is another problem, of course. So having the sparse point cloud, then the dense reconstruction process will significantly drop. As we can notice here, the PSR is dropped from 22 to on about 70. So that's a problem. So the dense reconstruction is related with the sparse one. So if we reduce the view number, it will reduce the performance significantly. So this validates the critical need for us to have enough data. Otherwise, we have to think in different ways. So this lead to my first work called few-shot 3D Gaussian splitting. And this work can reduce the required view number from 100 to just 3, just a few, yeah. So this work is already accepted by ECCV this year. So let's take a example about the densification process and how can we add the generative priors into the densification process to make the 3D reconstruction easier. Yeah. So given this L-shaped symbol, and we have two existing Gaussian we denoted as blue, and this is a viewing camera. So 3D Gaussian is trying to use the photometric information and say this is 3D, and we rasterize, we flatten them into 2D images, and we have the 2D observation. We compare the difference between the rasterized or rendered images and the existing observed images. We calculate the loss, and we backward the loss or the difference toward the 3D representation, and we guide the densification or how we clone some new Gaussian to complete this shape, right? So the original method using some heuristic rule trying to clone Gaussians based on the gradient only, but and the sparse view case is quite noisy for the densification process. So you can see it cannot clone the Gaussian point very accurately to complement the L shape. So that's why we're trying to get rid of the heuristic rule. We are trying to build a geometric graph build based on the 3D information. So here, still the L curve, we have two existing Gaussian, and we build the geometric graph and we connect them together. We build an edge between them, and the edge is built based on a so-called proximity score. We are trying to measure which Gaussian is more closer to which to find the closest neighbor. And having this, we put new Gaussian in the middle, and having the new placed Gaussian, we were trying to make it toward the right position, right? So let's come to the next phase. So now we got the initialization in the middle of the edge. And the next, how are we going to push it toward the most representative place? So here we use a generative power. And the generative power, the first thing is, it's not diffusion model, it's not the language model, but it's geometric prior model. So now we have a so-called monocular depth estimator. Given one observation, it will tell us the pixels, which pixel is closer to the camera and which pixel is farther to the camera. So that's why with this relative information, we can get the densification of this green new Gaussian. So you can see initialize from here, we can get it toward the most representative place. This we know from the monocular depth information. This Gaussian is more farther with this one, right? So that's why we can push the neural clone Gaussian to the most to the best way. Yeah. So having this, we can see by incorporating the geometric graphs and by doing the Gaussian encoding to put the new Gaussians in the middle of the edge and using the generative power, we can see this. We can look at this graph. So this is the metric. The if one method is more closer to the top right, which means it will better. You can clearly see our method not only the rendering speed but also the rendering quality. Our method achieve the best performance. Yeah, so we are almost about 1,000 faster compared with the previous neural radiance based method, and we are also the best one. I mean, we achieve about 5% higher in the visual quality. Yeah. So this is the conclusion. We improve the SSM from 0.69 to 0.74, and the rendering speed compared with the 3D Gaussian, we improve from 220 to 290. Yeah. Yeah, so now we are able to create the photorealistic 3D environment. This is the indoor case. We just use 3 images and we build a 3D environment. We interpret this video to show with you guys. And you can see with the 3 images, our method performs significantly better compared with the 3D JS, where you can see some artifacts, right? And compared with the NeRF-based method, they are quite slow and their performance is way lower. Yeah. And for the more complex outdoor case, let's take this example, and we can see we reduce the required view number from 200 to just 12. And we can also build a very photorealistic 3D environment, and we can bring a novel view for any simulation environment. Yeah. Yeah, so future Gaussian splatting help us to address the problem of how many views we really need to build a 3D environment. But still, if we review the entire 3D reconstruction pipeline, it's quite lengthy and it's a modular processing. So start given images, input images. We first do feature extraction and we match these features, and we do the geometric verification to find which is in layer and which is out layer. And then we will do the geometric initialization to initialize the entire thing. And the next, we will register more and more images into the global representation. And finally, we will do the triangulation to verify these points. So with the boundary adjustment, we will do the joint optimization for the camera and the scene representation. And the very last step is about the dense 3D reconstruction. So we can see it's quite lengthy. And from images to the recreated 3D environment, we have to go across about 10 steps. So ideally, if we learn from language processing or 2D images, can we have a single model, or can we have an end-to-end pipeline that build the 3D environment directly from 2D observations? Yeah, so if we're going to have some foundation future for the 3D vision, we have to learn the experiences from language model and vision model. Yeah, so that's an ideal case. But the ideal case poses us a lot of challenges. So given images, since we don't know any other information, we only have the pixel intensities. And we are going to estimate so many parameters. It contains the intrinsics, it contains the extrinsics, it contains the thin parameters. So we have millions of parameters to estimate based on the solely image observation. That's quite difficult. So this comes to my another work called Instant Splat. So Instant Splat trying to create the 3D asset just by second. Since previous method, they rely on dense image data, and their processing step is roughly 1 or 2 hours. So we're going to reduce the creation time by hours to just seconds. So this comes to our Instant Splat work. So again, 3D optimization problem it rely on an iterative optimization way to gradually estimate all these parameters based on the image observation. Yeah, that's a basic principle of 3D learning. But differently, our Instant Splat paper trying to connect the 2D observation and the 3D representation that we're going to build. We directly connect them together. We build the end-to-end operators between 2D and 3D. So specifically now from 3D to 2D, we use the differentiable raster. We can obtain the 2D images based on the differentiable operation. And then from 2D to 3D, we can use M-projection, which is also differentiable. So by connecting them together with the differentiable operator, we can define the loss function. So the loss function here is the first term. Let's see. The first term, I here is the observation. And we have the rasterized one. And the rasterized one use the G. G means the 3D representation. And T and K means the parameter that we're going to optimize. So we said that they are all learnable. And we're trying to minimize this function. And this function will return the optimal intrinsic, extrinsic, and 3D representation. But the problem is, if we directly connect them together from random initialization, it's very difficult for us to optimize since we don't know anything about the 3D environment. So that's why we rely on an a generative model that give us an initial depth information, and we got an initial scene representation. Let's take a look at the next page. Yeah. So here still start from the multi-view encoded images. We got the initialization, and the initialization is quite coarse. So let's see. Let me tell how coarse it is. So let's see. This is the initialization. If we directly use the initialization for rendering, we cannot accept this kind of quality, right? So now we build the end-to-end optimization just by 1 or 2 seconds. We can see the image got much more sharper. Yeah, it's quite clean, and all the optimization process just lasts for about 10 seconds. And boom, we got this 3D information, and all things are optimized in an end-to-end way. Yeah. So now let's take a look at some demos. So first, I gotta say I don't want to cherry pick any image data or metrics. I've got 3 images for this building, right? And I use my instant spread work, 3 images, and 10 seconds we build the 3D representation. So now you can think we are in the AR or VR headset. We are exploring in the purely virtual environment. We can see the image quality is quite high. We don't do any post-processing, and just our instant spread framework, we can build the photorealistic 3D environment. So yeah, this is a real case. Let's see how instant spread generalized to generated data. So this generated data is from Sora video. And we got this video, we extract 3 frames, the first frame, the middle frame, and the last frame. So having these 3 frames, we send it to the instant spread. You just think the instant spread is black box. And the output is the photorealistic 3D environment. We got this, yeah, 3 images, 10 seconds. And this is indoor case. Of course, indoor is kind of simple. So if we talk about outdoor, this is also from Sora video, and we can clearly see 3 frames. We also build the photorealistic 3D environment in 10 seconds. And this is render null view by interpolating the 3 images. Yeah. Yeah, so of course, we also have to look at a little bit about metrics, although it's kind of boring, but the visual quality, we can clearly see it improved nearly 100%. And the estimated code error is reduced significantly. And for the training time, we reduce from several minutes to several hours to just 10 seconds. And we can build the 3D representation very quickly. Yeah. So based on previous 2 literature, we have addressed 2 problems. One is the training view number, and another problem is the training time. Yeah, so now we are looking at more specifically, can we try to deploy the build 3D representation to specific hardware, let's say the headset. Since in the headset, the computing cost is typically it is constrained, right? So can we directly deploy them into the headset to explore the virtual world very easily? The answer is not yet. So the problem is this 3D representation is explicit 3D representation for each 3D primitive. I say for if we're going to use 3D Gaussian to model the environment, we have placed millions of primitives here. And for each primitive, we have to store them explicitly. And in this way, we have to more than 1 gigabyte for even just one thing. And it will also affect the rendering speed if we directly deploy the trained model into the headset. Yeah. So that's why we come to another work for the rendering efficiency. So the rendering efficiency means we have built a 3D environment, and then we try to deploy on a specific hardware, and we try to get the faster and the lighter representation when we explore in the virtual environment. So like Gaussian trying to compress the 3D representation by 15 times, And we are also improving the rendering speed by more than 60. Yeah. So for this time, let's first look at the metric also. Yeah, so we can see bottom, that's most state-of-the-art 3D representation, which is 3D Gaussian. And it uses more than 1 gigabyte. And the SSM value is about 0.85. The higher, the better. Yeah. So the bottom one is ours. We compress the model by more than 50. And now we can see the video quality is very close to the baseline model. We do a very, very competitive comparison here. So the bottom one, this side is our method, and this side is the baseline model. We can see they are almost the same. We cannot tell any difference. But if we look at the metric in the right figure, we can see for the rendering speed, we improve by more than 60, and we got very comparable video quality, and our model size is way lighter. So let's first review the intrinsic problem of the 3D Gaussian. So for the 3D Gaussian, we have millions of primitives to model the environment. So that's why we have to store them individually for each one. And the next problem is, since in 3D, we have to model very complex lighting condition, let's say the specular light. So that's why we have to use the spherical harmonics to model the lighting condition. And the spherical harmonics is very heavy. So for each 3D Gaussian, we will have more than 50 dimensions. And then you can imagine, so how many storage is required for this, right? And the last problem is it's explicit representation, and there are no quantization techniques for this representation. And we have to store each primitive individually, although they are maybe very, very similar, but still we have to store them individually. So that's why we trying to use some machine learning techniques and bring them to computer vision, to graphics, right? Yeah. So in machine learning, they are trying to make the model to be lighter, to be faster based on the pruning technique. So given a dense machine learning model, just like that, we have densely connected neurons, and we calculate the importance score between each connection. And having each connection, we will measure the significance or importance of each neuron. And based on the significance, we can prune the redundant or less important neuron. Then we got the sparse model, sparse ML model. Now we can see after the model pruning from dense to sparse, the model gets lighter and faster. So can we also build the criteria for 3D learning or 3D representation? So now you can think this 2D is just pixels, but 3D is each 3D primitive. So for 3D primitive, we have the concept about ray. And can we build the criteria based on this intuition? So that's why come to the next page, 3D importance score. So now still we have the image, we have the camera, we capture this image, and we can show the ray between the camera origin and each pixel. Now we have the 3D, the concept of 3D ray. And next, we have the initial 3D representation. It's dense 3D representation. We have each primitive individually. And we are going to calculate the importance score by shooting ray from camera origin to each pixel and calculate the importance score based on their relationship from each ray and each 3D primitive. That's a basic idea. And now we will look at, after the pruning, we will have a sparse 3D model. And the sparse 3D model is faster, it's lighter. Yeah. So but the first problem, how can we do the calculation? Of course, we can calculate it, but it's in the 3D space. So now we are going to talk about, we shoot the ray, and for each ray, we will compute whether they are intersect with the 3D primitive. So if they are intersecting, which means when they do the 3D to 2D rendering, they are affecting each other. So which means they are more important. So that's why the first item here is about the concept of hit count. So the intersection between each 3D ray and each 3D primitive. And the next is about the opacity. Let's say how transparent is the Gaussian, which means if a Gaussian has higher opacity, typically it means it will contribute more to the rendering process. So we will assign a higher weight. And the last term is about volume. Let's say if there is a larger Gaussian, we will place more importance on the larger one. If there is a very small Gaussian, we will place less importance on that one. Yeah. So combine them all, we can have the important score in 3D. And now we can see the x-axis is the Gaussian point ratio, and the y-axis is the red curve. That's a SSM value. We can see even we prune nearly 60% of the Gaussians, we still preserve the visual quality very well, which means the original model is quite redundant. Yeah. So if we look at the blue curve, which means after pruning, the FPS is consistently improving. So that's why we want to prune as more as possible. So now let's see, we have the conclusion in the first part. Sorry, let's move to the second part. So having a teacher model and having a student model, that's in machine learning literature. But if we bring to the computer vision and computer graphics literature, so can we think this way? So having a teacher model that is equipped with more knowledge with a higher spherical degree, it models the lighting very well. But for the student model, we use a smaller degree for the spherical harmonics. And then we're trying to input the knowledge. We transfer the knowledge from teacher with a higher degree to the lower student, to the student with a lower degree of the spherical harmonics. Yeah, we don't want to directly use just images to training, but we want to transfer this soft knowledge between the teacher and student. So that's why we can remove the redundancy in the spherical harmonics coefficient, and we got a light representation. That's in the second perspective. And in the last perspective, it's a very representative technique called vector quantization. And we apply the vector quantization on the spherical harmonics since they are most likely more redundant. And we also use the importance score to measure which attributes or which primitive we are going to apply the vector quantization, since we don't want to touch those 3D primitive that's quite important. We only want to reduce those redundant one. Yeah. So combine them all, we can see. So this is the metric. Our metric improved the FPS from 130 to about 230. And our size reduced about 15 times. And if we look at visual, not only for the outdoor, but also for the indoor, we are perform very similar with the baseline, but we got 16% faster, 60% faster in the running speed, and 15 times in the model size. Yeah. And this is some demo. Yeah, demo is always very interesting when we get the images and we build the 3D environment. So this is a navigable 3D environment. So that's why you can see we can move forward and we can move backward, and yeah. So we can play a lot of spatial demo with the build virtual 3D world. And of course, the previous one was done when I was a full-time engineer at Alibaba Group. But for this demo here, I got them from Twitter. So you can see the background is synthetic. We are trying to they are trying to get images and build the synthetic environment and to train their robotic policy. And the last demo is another paper called 6DGS. So you can see they can apply the 3D Gaussian or spatial computing techniques into the medical imaging, and then we can do more interactive demos with the medical visualization. Yeah. So next part, we're going to advance to the virtual reality industry. Yeah, but let's first how the generative AI can revolutionize the virtual reality industry. So let's talk about the generation of the foreground object and the background 3D scenes. So we can see the foreground object is generated, and we can play them by using our handle. And for the background, it had to be 360 or field of view. Since it's in the virtual environment, we will move our head around. We don't want to see any view that is out of the generated environment, right? It had to be immersive. And we also want to walk around in the generated environment. That's why we have to require a 3D environment for this generation. So with these two requirements, we're going to use generative AI for 3D panorama generation. Yeah, so in the 3D panorama generation, it's pure 360 field of view. And it's also a 3D environment so that we can play with it. But let's first review the existing generative models. The first is diffusion model. The diffusion model trying to generate a 3D object from text description. We can see it generates good quality for the 3D object, but if we talk about thing, it cannot generate very well. And the next paper is called Neuralift 360. That's our paper, and we are building the 3D models of the input single image. Yeah, it's image-based generation. But still, the image-based generation can only generate the house. The house is not large enough for us to do the immersive interactions. So that's another work called Lucid Dreamer trying to handle the scene scale generation. So since we don't have the panorama data, they start from a perspective or just a normal image, and then they gradually do the outpainting to outpaint more and more image content and to enlarge the field of view. But still, it's very difficult for the outpainting method to cover the entire 3D representation, 3D world. So that's why we have to use the panorama, explicit panorama format. And then we will talk about the DreamScene 360 and the 4K4D gen. So for the first paper, DreamScene 360, that's already accepted by NeurIPS this year. And this paper can try to generate a 3D panorama based on the text descriptions. Yeah. And the 4K4D gen extended from DreamScene 360. And now we can generate the 4D environment. I mean, there is some dynamics, animatable dynamics in the 3D environment, which is called 4D. And we can scale the resolution to 4K resolution. Yeah. So the first problem is the data scarcity in panorama format. So in 2D images or 2D generation, we have Line 5B, which have billion of data to train a foundation model for this generation. And even for 3D object generation, there are about 10 million of data. But if we talk about panorama, here we only have about 100 good quality annotations for in the panorama format. So we can also think it's very difficult for us to get the panorama and then annotate very high quality annotations, and it's diverse. It's very difficult for us to do this kind of annotation. So that's why we have to use the generative process in 2D and in geometric learning to do this generation for panorama. And we will use different model, and we will use monocular depth estimator for this generation. So first, for 2D panorama, we're going to mention one paper called multi-diffusion. So normally, given a panorama image we want to synthesize, the most easier way for us is to split the panorama into non-overlapping patches and diffuse them individually. But clearly, we got inconsistent results. So the multi-diffusion proposed to use the sliding window, and they are trying to average the overlapping region. So that's why you can see the generated panorama in the pixel space is consistent. Okay, having a 2D panorama, how can we build the 3D information? So first, we don't have the depth. I mean, the 3D, at least we have to have the depth information about the 3D environment. So given the panorama, and how can we estimate the depth? So now we are using the neural 3D reconstruction technique that we have a neural network, which is an MLP. And the MLP, the input is a view direction, since panorama is literally a single image and it's 360 degree of view, right? So now we are conditioning the view direction for the input of the MLP, and the output is a perspective depth value. We split the panorama into multiple overlapped perspective image, and having this image, we can use monocular depth estimator, which is well trained. And we are trying to use a neural network to memorize all of these monocular perspective depth information. And then during after the training, we can use the information within the MLP to render any depth value of the 3D environment. Yeah, so having the panorama, having the depth information, now we can see the left side give us the panorama, and this side give us the panorama depth. Now we can initialize the 3D Gaussian. So 3D Gaussian is a good way to do the neural learning. And later we will reuse some technique in our previous few shot perspective paper to augment during the optimization process and apply the guidance. And finally, we got the 3D representation. So if we take a look at the demo, given a very simple text description, let's say a stunning city in my dream. Now we will have a ChatGPT help us to complete the description. it will make the description more finer. And then we will generate the panorama in this way. And having the 2D panorama, we lift it to 3D using the neural 3D reconstruction technique. And now we can see this is the virtual 3D image. We can jump into the virtual, and we can rotate our head, and we can move forward, and we can move backward, and even we can move upper and lower. Yeah. So everything can be rendered at real time at this moment. So that's why the spatial computer is really closer to our daily life. Yeah. And this is another demo. Since this is submitted to ECCV this year, and they are held in Italy. So that's why we generate a panorama image for the ECCV. Yeah. And then we got the 3D representation just like this. And then we can move forward into the pure 3D information, 3D representation, and we can move around and we can play with. Yeah. So we can clearly see the DreamScene 360 provide us a solution that we can generate 3D panorama representation. And now we are going to generate the dynamic panorama, which means we're going to have the dynamic information, and we can see some motions during the virtual environment. So our innovation in this page, in this paper, Focus Vision, we submitted this paper to ICLR this year. So we use a animation foundation model to serve as a diffusion process. And then we split the panorama into the overlapped patch, and we diffuse them using the animatable pairs and inject it into the input static panorama image. And finally, the panorama image is dynamic. Now we can see this is the input static panorama. They are same resolution, but I'm trying to hide the details of the dynamic one. We can see there is some physical plausible motion by distilling the knowledge from the foundation diffusion model. And we can also see here, there are also some motions. They are very photorealistic. And the next thing is, this is a 2D video. We have to lift them into 4D representation. Now, we not only have the depth, but we also have the spatial difference. Yeah, so the temporal difference. So now we are talking about, given the panorama video, we apply the spatial temporal alignment based on the same neural 3D reconstruction, but we add additional regularization since we have the temporal dimension. We have the movement in adjacent frames are consistent. So after adding this regularization, now we can see this is the static panorama. They are static and it's at 4K resolution. Now we build a 3D representation. We can render 500 by 500 images. It's at different angle. We can still see the rendered image is quite sharp. We can see many details here. And we can put this 3D representation to the VR demo, and we can, that's why we can, before the demonstration of this page, we see some very interesting demo, and that's from my collaboration with the Meta Reality Lab. I'm trying to integrate my generative work on panorama generation into their headset. Yeah. So having talked about the 3D learning with the generative AI, which is very important part for my research careers. So in the future, and my current work are trying to integrate the 3D learning with the robotics, with the medical imaging, and with the human modeling. So with this, we can achieve very fancy and important applications. So let's take a look at the first one. So we are trying to develop the semantic 3D foundation model. So the semantic 3D foundation model get rid of the optimization 3D learning. Now we're trying to make the 3D reconstruction to be data-driven. So given images as input, we don't know any information, and we build the 3D information. We build the 3D semantics by a feed-forward way, and everything can be done in 0.2 seconds. So having this, we can imagine in the future, for robotics, we don't need to explicitly estimate the camera angles. And at the same moment, we can have the semantic information at very well. And then our ongoing work is trying to align this paper is called Large Spatial Model on NeurIPS this year. And now we are trying to align the spatial knowledge in the large spatial model and trying to align with the language model. Since the language model have the general knowledge about, let's say, if we ask the robot to go to a restroom, it has it can decompose the task into several subtasks and then execute every subtask individually. And our spatial model will provide the accurate spatial and semantic information to guide the robotic learning. Yeah. So the second part is about semantic. The 3D foundation model can help the robotics for tracking and mapping. So this AROS paper integrated the foundation model in the system. And now we don't rely on the input camera pose. We don't rely on the LiDAR as input. We can build the 3D tracking and mapping in real time, and we got very accurate quality. And the next part is about controllable simulation. So for the generation side, of course, it's very interesting, but now we want to add more controllability. And let's say we can, of course, reconstruct and generate the background. And we synthesize one of the pedestrian here. Let's say, can we generate some auto distribution motions? And we can generate some avatar. And we place this avatar into the virtual, the physical plausible digital world. And now you can see we place this pedestrian with this pedestrian, and its action is the motion is purely generated. So in this case, we can generate motion, we can generate the avatar to train the autonomous driving system more robustly. Yeah. So as we reach the conclusion page of this talk, so I'm really excited to the progress in 3D learning and spatial computing. So this technology definitely they will change the way we live, as they are the bridge between the physical world and the digital world. And really thanks for the listening, and I'm ready to any question you might have. Yeah.
Any questions online?
So I have a question. So hi, Joan. So
Hey.
can you hear me?
Yeah, I can hear you.
Okay, so I'm Bang. Yeah. So actually, I also work in Gaussian splatting. So, but I more focus on the dynamics parts. So I have a question that you try to distill the spheres from because the sphere takes a lot of storage when it comes to the Gaussian splatting, and you try to distill it from higher dimension to lower dimensions. But how did you decide how small you are enough to?
Yeah, so
balance?
I got the question. So that's also one application study in our paper. We're trying to, let's say the original one is 3 degrees, and we are trying to distill with the 2 degree and 1 degree. So what our observation is the 2 degree is sufficient, but if we consistently reduce the degree to 1, it is insufficient to model the specular light. So that's why we stop at 2.
Okay, so it is a hard line that for everything you just try to distill into.
Yes, yes. So I gotta say for the original 3D Gaussian splatting, they use 3 degree. I also believe this is the empirical number, but from our observation with the distillation technique, we can at most reduce it to 2.
Okay.
Yes.
Okay. Pretty cool. That's the first question. Second question is that I do like the instance splat. I think that works, though it hasn't published to any conference, but I think it is quite influential in the community. But I realized that I have heard about some discussion in the community that the instance splat, though it has a nice balance between the efficient and the quality, but when there come to a lot of views, actually the speed is much slow.
Yeah, that's a great question. So that's why we have another CVPR submission this year. Now we are going to lift a video to 3D representation. And you can think of the system is a black box, and having a video, we can lift the video to 3D representation by just a few minutes. And you can think this is an extension of the instance splat. So I gotta say instance splat is an initial work that's trying to directly bridge the 2D and 3D. But of course, it has depend on some initialization. So as well as it can provide a good initialization for dense view, I think instance splat could also extend to at least maybe 20 or 30 images. That's very easy. But for now, for our another submission, we call it a video lifter, and we extend this to arbitrary long video. Yes.
Okay. Pretty cool. And I have the last question that, so
Yeah.
that is a general question. So when I was trying to train the Gaussian splatting, I have always, no matter what kind of either the static thing or the dynamic thing, I have encountered the problem of the overfitting. That for a single object, but in the end, after you train it, there might be duplicate number of the Gaussians from different views. So that kind of overfitting, is there any general idea how to reduce such kind of overfitting?
So that's I think I can send you about the instant splat paper later. So our updated version trying to avoid this problem. Now, let's say given the input images, we initialize point-wise point-wise initialization, and we also have a masking strategy that we don't want to add the repeated points, and we don't use the adaptive density control, which means how many points are initialized. Then the final optimization we will also have the same number. So at this moment, we don't. I think you can get rid of the repeated pattern again. But
Okay, so that is a more stronger regulation, a little bit like depth.
Yes,
Okay,
yes, exactly.
So
Yeah.
pretty cool. Yeah, thank you very much. Yeah.
Thanks for the insightful questions.
Any other questions? Thank you very much.
Really, thanks for the attending. Thank you. Okay, I will stop sharing.